previous lecture, we talked about unsampled trees. And unsampled trees, we use them to improve stability of the model and reduce overfitting, also to enhance predictive performance. So that's why we are using unsampled trees, because the single trees are sensitive to data changes. To do this, we talked about 3 types of unsampled trees: the bagging, and the random forest, and the boosting. In this example, we'll be covering 2 of them, the bagging and random forest. Studies have found that many companies plan to continue allowing their employees to work from home after COVID. One of the managers, he has 200 employees, and we have variables like includes whether the performance rating of the employee improved from the previous year. If it is improved, then the performance per variable is going to be equal to 1, otherwise it's going to be 0. Also, the information contains the employee's age and income in thousands, and whether the employee has a managerial position or no. 1 if yes, no if otherwise. So the 3 questions, or the 3 parts of the question, says create a bagging unsampled classification tree. So it's a classification tree to predict whether an employee will achieve an improved performance rating after working from home or no. What are the accuracy, overall accuracy, sensitivity, specificity of the model on the validation data if the cutoff value of 0.6? So the question asks you to change the cutoff value. So the cutoff value, the normal one, if you use the confusion matrix, it's 0.5. So that's why we have to now to specify specifically the cutoff value by 0.6. We are going to repeat this by using random forest technique. And as you remember, random forest asks you to select some variables every time you grow a tree. You do not grow trees using all of the variables. There is kind of a rule of thumb used in this kind of trees, which is square root of number of variables. If you have, for example, 16 variable, you take square root, then you choose 4 variable every time you grow a tree. For instance, right now we have 3 variables, predictor variables. Then you take square root with 3 is 1 point something, because we cannot grow a tree with 1 variable. So we say 2 variables. That's why the question says select 2 variables, 2 predictor variables randomly to construct each weak learner. Weak learner, maybe I forgot to say something about this. Weak learner is the tree, single trees. Single trees, we call them like weak learner. So every tree is a weak learner. So that's why these trees, the unsampled trees, they use all of the weak learners to build a strong learner. Also, we have to find the overall accuracy, sensitivity, etc. And we will do the same thing, the cutoff value is 0.6. After that, we're going to compare the models. And the best way to compare the models is using the curves. Yes, using the cumulative lift curves, also using AUC value. So let's do that. First of all, we need these libraries. We need caret, gains, PROC. We need random forest, and also you can add rpart. Random forest is the one that you have to install the packages for. Others, I guess you have them, but we want to make sure that the packages are installed. Then we are going to install the data, right? So this is my data, work from home, chapter 13. And I'm going to look at the structure. Because I have 2 numeric, performance and management, it's a classification tree, so it's a good idea to change them to factor. Performance management, I'm going to change them to factor. So we change now the performance management to factors. So now we have 2 levels, 0 is 1, 0 is 1, and the age and income, both of them are numeric. After that, we partition them the way that we know. Set seed any number you would like, 1, 10, 1, 2, 3, as you like. So I have now my data, I have training, I have validation, 1, 20, and 80. You can have a look to your data. After that, we are going to build the bagging tree. Again, let's set the seed first to something, let's say 1, 2, 3. And bagging tree, call it bagging tree. The function is going to use called random forest. Random forest. So first we are going to specify the formula, which is the performance, all of the variables. Then we are going to specify the data, which is the training data. After that, we want to specify a number of the trees that we are going to grow. How many trees you would like to grow. You can set any number. Try to set like big numbers, let's say 100 or 200 or something, or 500 probably. Also, tell me how many variables you would like to randomly selected in every time we do a split. So this is the MTRY, because we have 3 predictors, and this is bagging. So in bagging, we use all of the variables to build each tree. So it's a 3. We can also include the importance factor or importance argument. So this one will tell you, or this actually indicates whether or not the variable importance measures must be computed in the model or no. So when we say true, that means the model will calculate and give you the importance measure. After that, we can print the bagging tree. We can print this. So after this, let's run. Let me go up. Random forest, where is it? Fine. I just ran or loaded the libraries again. So you got this. We have the formula now. Then you have type of the random forest, which is a classification. Number of the trees, we have 100. Number of the variables and at each split, which is a 3. Then you have out of bag estimate of the error rate, which is 24%. This is an estimate of the model accuracy using the samples that were not used in the creation of each individual tree, which is 24%. And we have the confusion matrix, 0s and 1s. But this is for the, for the training data. We usually create confusion matrix. We care about the confusion matrix in the data, in the unseen data, which is the validation or testing. So what we have to do right now, we have to look at the performance of the tree or the random forest tree on the validation set. By the way, we cannot visualize the random forest tree. We don't have access to any of the trees visually here, or it doesn't make sense actually, because the idea is to look at the final model. So because the question says we need to have a cutoff value 0.6, we will be using the probability, and we will be finding the class and the probability. So let's find the predicted probability. And I'm going to have underscore B because it's for bagging, because we're going to repeat this for a random forest. So it's going to be predict bagging tree, and on the validation, then the type is probability. So this will calculate the probabilities, right? We'll calculate the probabilities. After we calculate the probabilities, and again, we did this multiple times. If you copy this and see what this guy give you, you will have 2 columns. You have 2 columns, the first column and the second column. We said let's focus on the second all the time. And if the second is greater than 0.6, then classify this case to be 1. If it's less than 0.6, then classify it as, 0. So that's why we're going to create the cutoff values now. Let me create the cutoff as factor, because we need the cutoff value to be as a factor. If else, if the previous predicted probability for the second column, let's use one of the columns. If this value is greater than 0.6, it's greater than or equal, let's say, 0.6, then please give me 1. Or classify it as 1. Otherwise, classify the case as 0. After that, after we do the cutoff value, then we can add this to confusion matrix. Now we have the cutoff value, the cutoff, because now everything is classified, all of the cases are classified, and you can't try this, you can just copy this. It's going to give you a list of values, 0s and 1s. Do I have something wrong here? Oh, I did not run this guy yet. Let me run this. After that, I'm looking for the cutoff value. So this is the cutoff value. It just classifies all of these cases into 0s and 1s. Then we are going to come to this. So this is the predicted classes. This is the predicted classes based on the cutoff value 0.6. This is it. So again, it's a predicted classes. Normally what we do, we just calculate predicted class, and we do predict, bagging a tree, validation, and that's it. So this will give you predicted classes based on 0.5. But now, because we need to have a new cutoff value, so let's say let's give it another name: predicted class cutoff. we can say different cutoff, but I mean, just I don't want to have a long name. So the predicted class, and we are going to compare what we predicted versus what? The validation performance. And let's tell the confusion matrix that my positive case is 1. We need to know this because we need to specify the sensitivity and specificity, right? So running this will give me the overall accuracy, 70%. We have sensitivity, 71%, 67% specificity. And to tell whether these numbers are good or no, we need to compare them with other stuff, which is other model, right? So which is the random forest. In general, it should be better than the random assignment, which is good. So let's set the seed here for, I don't know, 1, 2, 3. Also, I'm going to copy these carefully. I'm going to copy the bagging, but I'm going to call it random forest. So I'm going to call it random. What did I call the other one? Tree. Random tree. Random forest tree. It's going to be the exact same function, the exact same formula, the exact same data. Number of the trees is 100, but every time you do a split, I don't want 3. The question says 2, which is 2. So every time you do split, you select randomly 2 variables, then you do split. After that, I'm going to look at the tree. So we run this, we got the same idea here. Number of variables tried every time, 200. The out-of-bag estimate of error rate is 22%, which is lower than the previous one, which is good. Also, let's do the predicted class cutoff. I'm going to call it random R. No, before this, we have to do predicted probability. Predicted probability not to be R, right? So, which is the predict random forest tree and the validation, right? Also, we need to specify the probability as a type or as a class or as a probability. So we need to do give me predict each case, or what is the probability for each case? This is it, using the random forest tree. After that, use this probability and tell me and classify them. How to classify predicted probability R. Take the second column is enough. Tell me if this one is greater than or equal 0.6. If yes, classify it as 1. If no, classify it as 0. After that, give me the confusion matrix. We need the confusion matrix for the predicted class cutoff R with what? With the original data, which is the validation performance. Predicted class cutoff R. Oh, I have here a problem. Here we go. Error in the confusion matrix. Let me validation performance. Let me try first looking at this guy. As factor, if else, predicted probability. So let me first look at this guy. I don't know if I ran the first one is fine. Then the second one is what's happening here. As factor, if else, predicted probability greater than 0.6, 1 other than the 0. Let me repeat. What's wrong? Let me go copy this. I don't know, maybe there's a small error. So let me here R. Don't tell me what was wrong. I don't know. So there is something, one of the maybe letters or something. So now we have the confusion matrix and statistics here. The accuracy is not better than the previous one. The previous one, we had the bagging, we have 70%, the overall accuracy. And it's kind of, these guys are flipped, sensitivity and specificity. The previous, the bagging one, we have here 70 something, here we have 60 something. So this is good because it tells you now which one you care more about. Do you care more about the positive cases or the negative cases? If so, you choose one over the other one. But let's compare both of them for part C. Let's compare both of them and do the gains table. Again, it's the same. I'm going to use the same code for the gains and cumulative lift chart. We care about having higher area. The higher area is better. So let's look at the, what do you call it? Cumulative. But before we do the cumulative, we have to specify we have to get the performance because we need it as a numeric variable now. So validation, we did this many times, performance as numeric. But again, to keep the 0, 1, we change it as character first, then we change it to numeric to keep the zeros 1. Then we're gonna make the gain table for bagging and gain table for the random forest. We did this guy. So we are using a gain table for the bagging, its gains function, the validation performance, and we are going to look at the second column of the predicted probability B. So I did not run this. Now we go. Here we go. So this is the gain table for the bagging, and we're going to do the same thing. Let me delete this because we don't need it. I have it. The gain tables for the random forest, and we have the validation performance, and we have the predicted probability random forest for the second column. After having these values, these are kind of two tables, and we have many values. After that, we create the cumulative lift chart for both of them. This is it's not hard, but the first one, we have no problem with it because it's the plot. Now we are going to plot the cumulative lift chart for the bagging. So this is the first vector from 0 to this value, and we talked about this. And this is the y value, and this is the x value. The range of the x from 0 to gain table B at cumulative observations, which is the data sign. This one, where is it? Cumulative observations. Yeah, these guys. So also the x lab, we're gonna call it the label, number of cases. The labels of the y, we're gonna call it cumulative. The color of the curve, we're gonna choose any color, green. And the title is going to be cumulative lift chart. The type, we have to see a straight line. So this is my plot for the bagging. If you create in R, if you create a plot and you can attach any other lines or any other plots to them. Like if you can add different lines, you can add other hatches or other, let's say, paste other stuff. So we are going to add another line that represent the cumulative lift chart for the random forest. So I'm going to use the lines function. Before, if you remember, before we had only this chunk and this one, which is the random assignment one, the red one, if you remember, the one that comes diagonal. But now I am adding another one. The order is not important between these two things. So I'm going to add another line, which is the blue one. This one will be representing the random forest. Again, I'm specifying y values, the vector, and x values for the random forest. I'm specifying the color, it's going to be blue, and the time is going to be straight line. Also, we have the main diagonal, which is the random assignment one, or the random assignment, which is the diagonal one. So after running this, we're going to look at the random forest versus the bagging. The first one is the green one, and the second one is the blue, and both of them are better than the random assignment. This is number one. Number two, you can tell me which one has more area. The idea is look at the area between the area between the red and the curve. So which one do you think covers more area? It's clear that the green one does better than the blue one, because the area under the green is bigger or higher than the area under the blue. So that's why this tree is doing better. Which one is the green? Is the bagging. So the bagging, generally speaking, is doing better than the random forest in terms of the cumulative lift chart. What about the AUC? The AUC, we can find the AUC for both of them using the ROC function, ROC function. So the first one, we can call it ROC object bagging. The other one, ROC object random forest. Then the first one, we have validation and performance. Then predicted probability, the way that we used to do it. Then we run this, we look at the area under the curve. And again, the bagging one has area better than the second one. So the values of the accuracy and sensitivity specificity with different cutoff values for the first one does much better than the second one. 77% versus 75%. So overall, we can say, based on both charts, the cumulative lift chart And based on the AUC chart, the bagging model, the green line, it seems to be, or it seems that performing better than the random forest, the blue line. And the AUC for the bagging was about 77%. For the random forest is about 75%. So the bagging is still is more robust, also according to the AUC. So we can actually conclude this and write the conclusion, which is the most important thing. So this for part C, or the conclusion. Let me type this down and let me type this down and continue or finish the question. So this is the conclusion, and yeah, that's it.